Okay, this is the first video about geometric optimization in calculus. The basic idea is that we are given a situation that we have to mathematize. We're not just given an equation that we can maximize or minimize, we're given a real situation, like the one we have here. We want to minimize the cost of manufacturing a box, a rectangular box, and the box has to hold 256 cubic meters. So this, you could imagine, is actually a possible real situation. And what you have to do is draw a diagram, assign variables, and write the equations that represent what we know and what we must optimize. Here in this problem, we drew a box. It represents what the problem tells us. The base of the box is a rectangle. One side is twice the length of the other side. One side is twice the length of the other side. Nothing is said about the height, so that gets a different variable. And finally, we learned something about the cost of the materials. So we're going to need equations that represent the volume that is fixed at 256 cubic meters, and the cost, which comes from the materials, the sides, the top, and the bottom of the box that are purchased out of materials that cost a certain amount per square meter. That's the biggest part of the problem here. The second step that we have to do once we have all the mathematizing done is we have to make sure that the function we're optimizing is a function of one variable. If it isn't, we have to do a substitution. And finally, the last step is the easy step. That's the calculus, where we take the function we're optimizing and we take its derivative and we find the critical values and we figure out whether they're maxima or minima, and we can answer the question using the calculus that we know. Okay, so let's begin. So the first thing we know here is that the volume of the box is the area of the base times the height, 2x squared. Oops, I'm going to make sure that x squared looks good. 2x squared times y, and there has to be 256 cubic meters. That's a condition we have to meet. That's also likely to be an equation we can use to make a substitution. The next thing we have to deal with is how we're going to figure out cost. Cost is based on the part of the box that we're looking at, the area of each of the sides, the top, the bottom, the front and the back, the left and the right. So we look at the area of each piece first, and then we'll multiply it by the cost of that piece. So the area of the bottom and the top is 2x squared. Each of those is 2x squared. And the area of the front and the back, the front and the back, is y times 2x, 2xy. And finally, the area of the left and the right is xy, xy. And we have two of each of these sides. Now the cost function, the only thing that's going to be different is that the bottom, the area of the bottom times $6 per square meter is different, because only the bottom costs that much. So this is the cost of the bottom of the box, and it's $3 a square meter for everything else. The top Now we have the front and the back. We have 2 of these. So that's 4xy. And the left and the right are the same, 2 of those, 2xy. Now we have a cost function, we just have to simplify it. So here, 6 times 2 is 12x squared, plus 3 times 2 is 6x squared, plus, then we have 4xy and 2xy, 6xy, divided by 3. So 18. You have cost as a function of 2 variables, and we need cost to be a function of 1 variable. So we have to go back and look at our volume equation here, and notice that we can solve for y or x, and substitute back into here. Now, if we solve for y, it's pretty straightforward. We divide both sides by 2x squared. But if we solve for x, we have to solve for x squared and then take a square root. And a square root always has a positive and negative answer, and that creates a complication. So why don't we solve for y? We have 256 equals 2x squared y. So y equals 256. Oh, I wrote 125. 256 divided by 2x squared. Simplifying further, y equals 128 over x squared, or 128 x to the negative 2. Sometimes it's more convenient to have the denominator. Sometimes it's more convenient to write it as an exponent. We're just going to scroll up a little bit so that we have room to continue. We're going to substitute this value for y into this equation. So now we're really going to have cost as a function of x is 18x squared plus 18x times 128 x to the negative 2. Now this is x to the 1. And x to the 1 times x to the negative 2 is x to the negative 1. So my cost function is 18x squared plus 18 times 128 x to the negative 1. Notice I'm not worrying about multiplying yet because it doesn't make a difference right now. Now I have a function of x and I can take the derivative. I can finally do step 3. So c prime of x equals 2 times 18, 36x, minus, because we're using the negative 1 exponent, minus 18 times 128 x to the negative 2. Now we have to set this equal to 0. And this is where it's going to matter whether or not we express this as an exponent, a negative exponent, or a denominator. And it's going to be much easier to set it equal to 0 if we create a rational expression that has a single numerator and a single denominator. Now we want to put 36x over this same denominator. So first we remember that it has a denominator of 1. And all we have to do is multiply the numerator and the denominator by x squared. So we have 36x cubed minus 18 times 128 over x squared, the original denominator. And x is not going to equal 0. We wouldn't have any kind of a box if one of the sides was 0. So we don't have to worry about that. We just want the numerator to be 0. So 36x cubed minus 18 times 128 has to equal 0. 36x cubed has to equal 18 times 128. And divide both sides by 36. And we get x cubed equals 64. And that's going to mean that x equals 4. Now the question is that a minimum or is that a maximum? And how are we going to know? Well, we can do a second derivative test. We can look at c double prime of x. I'm going back to this version of c prime, so I don't have to use the quotient formula. I can just use the power rule over here. So the second derivative is 36. Now it's plus negative 2 times negative 18 is positive 36. 36 times 128, and then it's x to the negative 3. Now if we plug in 4 here, we have a positive number, and we're adding it to a positive number divided by a positive number. We're dividing by 64. So this is positive. You can put it in your calculator and plug in 4, but it's sometimes more powerful to just realize this has to be positive when x is positive. So this is greater than 0. So we're concave up. Concave up. And so we have a minimum. And now we just have to figure out what that minimum cost is. And we can come right over here to this part of the cost function and just plug in x equals 4. The minimum cost, oops, always have to remember to create a color from my pen. The cost when x is 4 is 18 times 16, 4 squared, plus 18 times 128 divided by 4. 18 times 128 divided by 4. And 128 divided by 4 is 32. So 18 times 16 plus 18 times 32 is 18 times 48, which is, and this is going to be in dollars, $864. And that is our minimum cost. That is actually the minimum cost of a box where the base is a rectangle and one side of the rectangle is twice the other side, and the volume of the box is 256 cubic meters. The base costs $6 a square meter, and the rest of the sides only cost $3 a square meter. Then our minimum cost is $864. Ta-da!